In 2019 February, a new vulnerability in runC was reported by its maintainers, originally found by Adam Iwaniuk and Boris Poplawski. It was dubbed as CVE 2019-5736. It affects Docker containers running in default settings and can be used by an attacker to gain root-level access on the host. Alexis Arai, one of runC's maintainers, found that the same fundamental flaw exists in LXC. As opposed to Docker though, only privileged LXC containers are vulnerable. Both runC and LXC were patched, and new versions were released. Initially, the official exploit code wasn't to be released publicly until 2019 February 18, in order to prevent malicious parties from weaponizing it before users have had some time to update. In the following days though, several people decided to release their own exploit code. That led the runC team to eventually release their exploit code earlier since, as they put it, the cat was out of the bag. This post aims to be a comprehensive technical deep dive into the vulnerability and its various exploitation methods. So what is runC? runC is a container runtime originally developed as part of Docker and later extracted out as a separate open source tool and library. As a low-level container runtime, runC is mainly used by high-level container runtimes to spawn and run containers, although it can be used as a standalone tool. High-level container runtimes like Docker will normally implement functionalities such as image creation and management, and will use runC to handle tasks related to running containers, creating a container, attaching a process to an existing container, Docker exec, and so on. To understand the vulnerability, we need to go over some proc basics. The proc file system is a virtual file system in Linux that presents information primarily about processes, typically mounted to proc. It is virtual in a sense that it does not exist on disk. Instead, the kernel creates it in memory. It can be thought of as an interface to system data that the kernel exposes as a file system. Each process has its own directory and procs. So let me demonstrate it. If we list files under proc, it shows some directories which shows some numbers. Those are the process IDs. So this is our process ID. We can what binary our process is running. Our process in running on bin bash, which makes sense. There is a special symbolic link called self. This symbolic link directs to the current running process. So this is proc file system. This is the vulnerability overview given by the runC team. It specifies that the vulnerability allows a malicious container to, with minimal user interaction, overwrite the host runC binary and thus gain root-level code execution on the host in two scenarios, either creating a new container using an attacker-controlled image or attaching Docker exec into an existing container which the attacker had previous write access to. Those two scenarios might seem different, but both require runC to spin up a new process in a container and are implemented similarly. In both cases, runC is tasked with running a user-defined binary in the container. In Docker, this binary is either the image's entry point when starting a new container or Docker exec's argument when attaching to an existing container. This is the method used by runC both for creating new containers and for attaching a process to an existing container. The researchers who revealed the vulnerability discovered that an attacker can trick runC into executing itself by asking it to run proc selfx, which is a symbolic link to the runC binary on the host. An attacker with root access in the container can then use proc runc pidx as a reference to the runC binary on the host and overwrite it. Root access in the container is required to perform this attack, as the runC binary is owned by root. The next time runC is executed, the attacker will achieve code execution on the host. Since runC is normally run as root, the attacker will gain root access on the host. The vulnerability may appear to contradict the way symbolic links are implemented in Linux. Symbolic links simply hold the path to their target. For a runC process, proc selfx should contain something like user sbin, runC. When a symlink is accessed by process, the kernel uses the path present in the link to find the target under the root of the accessing process. When a symlink is accessed by a process, the kernel uses the path present in the link to find the target under the root of the accessing process. So if I demonstrate it, what we did was, this is our process ID, this symlink contains bash. It is just attached to the binary. We think that this process is running inside the container when we try to access proc, self, x, which it just contains this host. For any other symlink that would be the case. That's how symbolic links work inside the containers, otherwise, it will all points to the host. This X link is a special one under the proc file system. This file system is a virtual file system. What it means is, files under proc don't really exist on this. We can think about this as an API. If we look at it, the size is 0 for all of them, so how does that make sense? It is like this, if I try to access this file, we can't see the size is 0 of this file. It is the same reason those files are like APIs for kernel processes. X file is also not a real symbolic link. It doesn't go for the real semantics that kernel go for regular symbolic link. The kernel just gives you access to the open file entry directly. Now, let's see how I did the exploitation using a detailed description from LXC, which is another container runtime, which has the similar flaw. This runC vulnerability was exploited in Docker versions before 18.09.2 and other products. For the demonstration purpose, I have installed a Docker version that exists this vulnerability. It's 18.06.1. And it is running on my CentOS 7 server. You can see here Docker is up and running. If you see the command for the POC, first, I build the container for the image for this POC. Then I run it and finally I execute it to run in bash. This is the repository for the POC. First I have to clone the repository. I have to go inside my repository and cd into the exec POC directory. So this is the cloned repository. Here are the commands we are going to run now. The first one is to build the image for the Docker file. Okay, then let's run the container. Here we run it regularly. This D flag denotes that we run it in background. RM denotes that we remove ourselves after this is done. So before we run the last command, let me show you what is inside the container. So let's execute the container without running bash, just sh. So this inside the container. So this inside the container. If I look at the bash image I created, it is not the real bash. It contains this string. This syntax called shebang. Developers are familiar with this syntax. Essentially what this means is, when we run this file, don't run it, instead run what is within after the shebang. So this is a common way to run scripts. So now let's see the shared libraries approach or concept. This shared libraries allows us to overwrite runC by simply running a malicious image. This shared library approach can be implemented to compromise the host through two separate methods. First one is when a user execs a command into an existing attacker-controlled container. Next is when a user runs a malicious image. As soon as it runs the malicious container, runC gets overwritten. That is why this is a more powerful exploit. This method utilizes dynamic linking. When a process is run, it needs some libraries. For instance, in C programming, it needs libc to input and output. In here you can see what dynamic links are using in runC. It uses few of these. When the runC process is executed in the container, those libraries are loaded into the runC process by the dynamic linker. It is possible to substitute one of those libraries with a malicious version that will overwrite the runC binary upon being loaded into the runC process. We can alter any of these libraries used in runC. But in this demonstration, we chose this one. First of all, we tell the Docker file, the entry point is proc self-x. Our Docker file builds a malicious version of the libsecump library. Actually, it downloads the source code for this library and adds some own code to it. Then compile the library ourselves. The Docker file appends the content of run at link.c to one of libsecump's source files. Subsequently, the malicious libsecump is built. The constructor attribute, a GCC-specific syntax, indicates that the run at link function is to be executed as an initialization function too for libsecump after the dynamic linker loads the library into the runC process. Since run at link will be executed by the runC process, it can access the runC binary at proc self-x. The runC process must exit for the runC binary to be writable though. To enforce the exit, run at link calls the exec size call to execute overwrite runC. In here it open proc self-x for reading and overwrite run. In here, we don't need a process to appear or stuff like that, we run an image and runC gets overwritten. In this POC it just switches runC binary with a programmed reverse shell. I have two SSH terminal here for the demonstration. On the right side we have the attacker computer listening and waiting for the reverse at port 2345. And on the left side, we have the host machine. In here I will create a temp file including a text called this is host. You can see runC is normal. First let's build our malicious image. This might take some time. Building the image is successfully done. And let's run our malicious image. You can see that several things happen on the left. First thing was, we opened runC for reading. Again, we opened it for writing and edited runC. Then shut down. On the right hand side you can see, attacker gained the reverse shell. And it gets root level access of the host machine. Let's check the file we made in the temp folder. As you can see, it can be accessed in the attacker's machine. If you see what is in the runC now, it contains the script reverse shell for 2345 port. Docker recommends immediately applying the update to avoid any potential security threats. This is the summary of the Docker Engine versions of Docker Engine Community and Docker Engine Enterprise that addresses the vulnerability.